The object crosses Neptune's orbit on a Tuesday morning in October, though it carries no awareness of Earth's calendar or the small blue world that orbits closer to the yellow star. For 4.7 billion years, it has drifted through the space between stars, a wanderer roughly the size of a city block. Tumbling slowly through the cosmic void at 17 kilometers per second, its surface, darker than charcoal, bears the accumulated dust of interstellar medium, microscopic grains of silicon and carbon that settled onto its frozen bulk during the long journey between stellar neighborhoods. Each particle of dust represents a story spanning millions of years. Grains formed in the death throes of massive stars, in the cold molecular clouds where new suns are born, in the collisional debris of ancient stellar systems that ceased to exist when the galaxy was young. 3I/Atlas, the designation astronomers will assign in the coming weeks, follows a hyperbolic trajectory that speaks of origins far beyond the gravitational influence of our Sun. Unlike the elliptical paths of native comets and asteroids, this visitor's orbit opens outward like a cosmic slingshot, carrying it on a one-way passage through the inner solar system before flinging it back into the galactic dark. The mathematics of its approach encode the gravitational signature of its last stellar encounter, perhaps with a red dwarf star 37 light-years distant, where it received the final nudge that sent it tumbling toward our neighborhood of the Milky Way. The precision of orbital mechanics reveals that this encounter occurred roughly 2 million years ago, when early hominids were learning to craft stone tools on a world that the wanderer would not encounter for eons yet to come. Its composition tells stories of stellar nucleosynthesis in foreign suns, chemical processes that unfolded in stellar cores where temperatures reached 100 million degrees, and nuclear fusion forged elements heavier than hydrogen and helium. Spectroscopic analysis will reveal nitrogen compounds and carbon-based molecules forged in the atmospheres of giant stars that died before our own solar nebula began to condense. The object's interior, insulated by 4 billion years of vacuum, preserves chemical conditions from the epoch when the galaxy was half its current age and star formation proceeded at twice the modern rate. Each molecule locked within its icy matrix represents a sample from the interstellar medium of a younger cosmos, when the heavy elements necessary for rocky planets were still relatively scarce and the first generation of stars was still seeding space with the building blocks of future worlds. The visitor's surface temperature hovers at negative 250 degrees Celsius, a consequence of spending geological ages far from any stellar warmth. At this temperature, water becomes harder than granite. Carbon dioxide freezes into crystalline formations that would shatter like glass at the slightest vibration, and exotic ices form from compounds that exist only in the deepest cold of space. Yet even at these extremes, cosmic radiation slowly works its chemistry, breaking molecular bonds and creating new compounds that cannot form under earthly conditions. The Wanderer's outermost layers have been sculpted by 4 billion years of galactic cosmic rays, high-energy particles accelerated by supernova explosions and stellar winds from across the galaxy. The visitor's approach awakens detection algorithms in ground-based surveys designed to catalog potentially hazardous asteroids. Automated telescopes in Chile and Hawaii capture its movement against the stellar background, noting the peculiar trajectory that distinguishes interstellar objects from the countless pieces of debris left over from the solar system's formation. The Catalina Sky Survey, originally designed to track Earth-crossing asteroids, registers the object's motion as an anomaly worth investigating. Its brightness varies in a regular pattern as it tumbles end over end, each rotation revealing different surface features to the watching instruments. The period of rotation, roughly 8 hours, suggests a body that has been gravitationally relaxed over cosmic time, its spin gradually slowed by the subtle torques of passing stellar encounters. The discovery represents humanity's third confirmed detection of an interstellar visitor, following the mysterious acceleration of one Oumuamua in 2017 and the more conventional behavior of 2I/Borisov 2 years later, each detection has refined our understanding of how often such encounters occur and what they might reveal about the broader galactic environment. 1. Oumuamua's strange acceleration, possibly caused by outgassing of exotic ices as it approached the Sun, demonstrated that interstellar objects might behave in unexpected ways. 2I/Borisov, more clearly recognizable as a comet with its developing tail and coma, showed that some visitors retain the pristine characteristics of objects formed around other stars. Now 3I/Atlas promises to add another data point to humanity's growing census of galactic wanderers. Only now, with improved detection capabilities and dedicated sky surveys, does the astronomical community begin to grasp the frequency of such encounters. The Large Synoptic Survey Telescope, scheduled to begin operations in the coming years, will detect interstellar objects at a rate of perhaps dozens per year, transforming these cosmic messengers from rare curiosities into a regular stream of information about the galaxy beyond our solar system. Calculations suggest that at any given moment, several interstellar objects pass through the outer solar system, most too small or distant to register on current instruments. The galaxy, it seems, maintains a constant traffic of wandering worlds, each carrying samples and stories from stellar systems distributed across hundreds of light years. The wanderer's trajectory carries it past the orbit of Uranus, where it briefly interacts with the planet's complex magnetic field. The encounter, lasting only a few hours, creates subtle perturbations in both the visitor's path and Uranus's magnetosphere, a cosmic handshake between objects that formed under different stars. The planet's gravity provides a small but measurable deflection to the interstellar object's course, while the visitor's passage creates temporary ripples in the charged particle environment surrounding the ice giant. These interactions, detectable only by the most sensitive instruments, add precision to calculations of the object's mass and density. 3I/Atlas becomes a messenger from this vast galactic ecosystem, a fragment of cosmic geology that has survived the journey between the stars to arrive, quite by accident, at the gravitational boundary of our own solar family. Its presence raises profound questions about the nature of planetary formation around other stars, the composition of stellar systems throughout the local group of galaxies, and the possibility that biological materials might survive the rigors of interstellar travel. Each measurement, each spectrum, each photograph adds to humanity's understanding of how matter moves through the galaxy and what stories it carries about the cosmos beyond our immediate stellar neighborhood. The mystery that accompanies this visitor lies not only in its chemical composition, but in the question of how many similar objects pass undetected through our solar system each year. Current estimates, based on the 3 confirmed detections, suggest that interstellar visitors outnumber long-period comets from the Oort cloud, making them a significant component of the material passing through the inner solar system. Yet their dark surfaces and small sizes make them nearly invisible until they approach close enough for detailed observation. The true population of galactic wanderers remains hidden in the statistical shadows of our detection capabilities. The irony settles quietly over the observational data. This visitor has traveled farther than any human artifact will reach for millennia. Yet, it drifts past our planet with the casual indifference of deep time. It knows nothing of the civilizations that track its passage, the instruments that measure its composition, or the questions it raises about the nature of interstellar exchange. It has witnessed the birth and death of stars, the formation of planetary systems, the collision of galaxies, and the slow evolution of the cosmos itself, all while maintaining the silence of absolute zero and the patience of geological ages. It simply continues its ancient trajectory, carrying its cargo of foreign chemistry toward an eventual exit beyond the heliopause, where it will resume its billion-year journey through the space between the stars, perhaps to encounter other solar systems in the distant future, other civilizations that might wonder at its passage and decode the stories written in its alien ice. The deep survey awakens in the pre-dawn darkness of the Atacama Desert, where automated telescopes begin their nightly scan of the southern sky. The Catalina Sky Survey has been monitoring near-Earth objects for decades. Its algorithms designed to detect the subtle motion of asteroids and comets against the stellar background. But the detection of 3I/Atlas triggers protocols designed for a different kind of discovery. Within hours of the initial observation, alert networks ping observatories across 6 continents, each facility adjusting its scheduling algorithms to accommodate follow-up observations of the mysterious visitor. The object's hyperbolic trajectory immediately marks it as extraordinary, a wanderer from beyond the gravitational reach of our Sun, following a path that opens outward toward the infinite rather than closing into the elliptical orbits that characterize native solar system objects. The European Southern Observatory's Very Large Telescope Array repositions its 4 8-meter mirrors toward the coordinates transmitted from Arizona, each telescope controlled by computers that compensate for Earth's rotation and atmospheric distortions, with precision measured in milliarc seconds. In the controlled environment of Paranal Observatory, 2,400 meters above sea level in the Chilean Andes, adaptive optics systems sample atmospheric turbulence 500 times per second, adjusting deformable mirrors to counteract the blurring effects of thermal cells and wind shear. The resulting images reveal surface details on an object smaller than most asteroids, yet traveling faster than any comet from the Oort cloud, its dark surface reflecting less than 4% of incident sunlight, making it darker than fresh asphalt and nearly invisible against the cosmic background. Only its motion against the stellar field betrays its presence, a slow drift across the constellation Sculptor that speaks of vast distances traveled and gravitational encounters with stars whose names exist only in astronomical catalogs. The visitor's apparent magnitude varies between 21st and 22nd, requiring exposure times of several minutes, even with the largest ground-based telescopes. This faintness results not from extreme distance, but from the object's small size and remarkably low albedo, characteristics that suggest a surface composition dominated by carbon-rich materials or organic compounds processed by billions of years of cosmic radiation exposure. The Hubble Space Telescope, orbiting 400 kilometers above Earth's atmosphere in a 96-minute cycle around the planet, receives priority target of opportunity scheduling to observe 3I/Atlas during its brief passage through the inner solar system, free from the distortions of weather and atmospheric scattering. Hubble's 2.4-meter mirror captures images with angular resolution limited only by the fundamental physics of light diffraction. Each exposure reveals new details about the wanderer's surface composition and rotation state, processed through spectrographs that separate reflected sunlight into its component wavelengths with precision sufficient to identify individual molecular absorption lines. The object appears elongated, perhaps 3 times longer than it is wide, tumbling in a complex rotation that suggests a history of collisions or tidal encounters during its journey through interstellar space. The rotation period, determined from the regular variation in brightness as different surface features catch and reflect sunlight, measures approximately 8 hours and 17 minutes, a value that has remained constant throughout the observational campaign, indicating a body in free rotation with no significant internal energy dissipation. This stability suggests either a monolithic structure or a rubble pile that has reached gravitational equilibrium over cosmic timescales. The visitor's spectrum shows absorption features consistent with organic compounds, carbon-based molecules that form naturally in the cold depths between stars, where molecular clouds provide the raw materials for complex chemistry at temperatures approaching absolute zero. Specific absorption lines indicate the presence of methane, carbon monoxide, and more complex hydrocarbons that could only have formed in the reducing environment of the interstellar medium, far from the oxidizing influence of stellar radiation. These compounds preserve chemical conditions from the epoch of the object's formation, potentially billions of years ago in a stellar system where planetary formation may have proceeded under very different conditions than in our own solar nebula. Ground-based radio telescopes joined the observation campaign, their massive dish antennas searching for any electromagnetic emissions that might indicate unusual activity as the visitor approaches the inner solar system. The Very Large Array in New Mexico. Its 27 antennas arranged in a Y-shaped configuration across the desert landscape detects faint radio signals at frequencies consistent with cosmic ray interactions on the object's surface. These signals result from high-energy particles, protons and atomic nuclei accelerated to near light speed by supernova explosions and stellar winds from across the galaxy, striking exposed ice and rock and generating electromagnetic pulses detectable across interplanetary distances. The radio emissions provide additional confirmation of the wanderer's composition and structure. The signal, strength and frequency distribution match theoretical predictions for cosmic ray spallation in a mixture of water ice, carbon compounds, and silicate minerals, materials that tell stories of formation in a stellar system very different from our own. The presence of silicates suggests that the visitor formed in the inner regions of its parent system, where rocky materials could condense from the stellar nebula, while the abundance of ices indicates subsequent migration to colder regions or ejection into interstellar space, while volatile compounds remained frozen. The mystery deepens with each observation as accumulated data reveal characteristics that challenge existing models of interstellar object behavior, unlike 2I/Borisov, which developed a visible tail as solar heating sublimated its icy components. 3I/Atlas remains stubbornly inert, showing no signs of outgassing despite its approach toward the Sun and steadily increasing surface temperature. This behavior suggests either a composition dominated by more refractory materials, compounds that remain solid at higher temperatures, or a surface layer of accumulated interstellar dust that insulates the interior from solar radiation and prevents the sublimation that typically characterizes cometary activity. Thermal infrared observations from multiple space-based observatories, including the recently launched James Webb Space Telescope operating at the Earth-Sun L2 Lagrange point, measure surface temperatures that remain consistent with passive radiative equilibrium. The object absorbs solar energy at wavelengths corresponding to its distance from the Sun and re-emits that energy at longer infrared wavelengths without the additional heating that would accompany active sublimation of volatile materials. This thermal balance indicates a surface that responds to solar heating in a predictable manner, without the complex energy budget that characterizes active comets or asteroids with significant internal heat sources. The international coordination required for comprehensive observation reveals both the capabilities and limitations of Earth's astronomical infrastructure in the early 21st century. Major observatories schedule precious observation time around the visitor's predicted brightness and position, balancing the scientific value of interstellar object studies against ongoing surveys for potentially hazardous asteroids, exoplanet transit observations, and deep space imaging programs. The scheduling decisions reflect not only scientific priorities, but also the practical constraints of operating multi-million-dollar instruments with maintenance requirements, weather limitations, and the competing demands of international user communities. Smaller facilities contribute photometric measurements that help refine orbital calculations and monitor the visitor's brightness variations with time. University observatories, regional telescopes, and even sophisticated amateur installations add data points to the growing database of measurements. Their observations coordinated through online platforms that democratize participation in cutting-edge astronomical research. The collaborative effort transforms the solitary wanderer into a focus for global scientific cooperation. A reminder that cosmic phenomena transcend the boundaries drawn by human geography and political organization. Amateur astronomers, equipped with increasingly sophisticated CCD cameras and computerized telescopes available for a few $1,000s, contribute light curves and position measurements that would have required professional observatory resources just decades earlier. Their observations, processed through standardized photometric reduction software and submitted to international databases, provide temporal coverage that complements the intensive but intermittent observations from major facilities. The distributed nature of this observational network ensures continuous monitoring despite weather, equipment failures, or scheduling conflicts at individual sites. Orbital mechanics calculations, refined with each new position measurement, reveal the visitor's most recent stellar encounter occurred approximately 2 million years ago, when it passed within the gravitational influence of a red dwarf star designated Gliese 445 in stellar catalogs. The encounter, reconstructed through backward integration of the object's trajectory and the known motion of nearby stars, provided the precise velocity change that sent 3I/Atlas on its current trajectory toward our solar system, a cosmic billiard shot played out across interstellar distances with gravitational cues and stellar masses. Before that encounter, the object likely spent hundreds of millions of years drifting through the local interstellar medium, accumulating dust grains and experiencing the gradual chemical evolution that occurs in the deep cold between stars. The visitor's trajectory carries it past the orbits of the outer planets with clockwork precision, its path determined by the same gravitational laws that govern planetary motion and spacecraft navigation, yet operating on scales that dwarf human engineering experience, unlike human-made probes, which carry instruments and communication systems powered by radioisotope thermoelectric generators or solar panels. 3I/Atlas remains silent, offering information only through the passive reflection of sunlight and the thermal radiation of its sun-warmed surface. It becomes a natural laboratory for studying interstellar conditions, a sample return mission executed by the galaxy itself over timescales that dwarf not only human civilization but the entire evolutionary history of complex life on Earth. Spectral whispers from afar emerge as Earth's most sensitive instruments dissect the faint sunlight reflected from 3I/Atlas, revealing chemical signatures that speak of stellar nurseries far beyond our solar neighborhood. The wanderer's surface tells stories written in molecular absorption lines, each dark band in its spectrum corresponding to specific compounds that formed under conditions impossible within our sun's gravitational domain. Infrared spectrographs aboard the James Webb Space Telescope detect the fingerprints of water ice mixed with carbon monoxide, methane, and more exotic molecules that crystallized in the frigid environment of interstellar space, where temperatures hover just a few degrees above absolute zero and stellar radiation remains too weak to drive complex photochemistry. The most remarkable discovery emerges from high-resolution spectroscopy conducted by the European Southern Observatory's Very Large Telescope Interferometer, where 4 separate 8-meter mirrors work in coordination to achieve the angular resolution of a telescope 40 meters across. The combined light reveals absorption features consistent with deuterated water, heavy water where one hydrogen atom has been replaced by its heavier isotope, deuterium. The deuterium to hydrogen ratio measured in 3I/Atlas differs significantly from the values found in solar system comets, suggesting formation in a stellar environment with different nuclear processing history. This isotopic signature provides direct evidence that the visitor originated around a star with different mass, age, and metallicity than our own Sun. Further analysis reveals the presence of formaldehyde, hydrogen cyanide, and complex organic molecules, including polycyclic aromatic hydrocarbons, carbon-based compounds that form naturally in the circumstellar disks around young stars and the photodissociation regions where stellar radiation interacts with molecular clouds. These compounds, preserved in their pristine state by 4 billion years of deep space refrigeration, offer a direct sample of the chemical inventory available during planetary formation in an alien stellar system. Each molecule represents a fossil record of stellar nucleosynthesis and disk chemistry operating under physical conditions that may have varied significantly from the environment that produced Earth and its neighboring worlds. The visitor's infrared emission spectrum, captured during its closest approach to the Sun, reveals thermal characteristics that challenge conventional models of small body composition. As solar heating warms the object's surface from negative 250 degrees Celsius to merely negative 100 degrees, certain spectral features strengthen while others fade, indicating complex phase transitions and chemical reactions occurring in real time. The thermal response suggests a layered structure with different compositions at varying depths, perhaps indicating multiple episodes of material accretion during the object's interstellar journey or heterogeneous formation conditions in its parent protoplanetary disk. Polarimetric observations, measurements of how reflected sunlight becomes polarized upon scattering from the visitor's surface, provide additional clues about its physical structure and composition. The degree and angle of polarization vary systematically with the object's rotation phase, indicating surface regions with different grain sizes, compositions, and optical properties. These variations paint a picture of a world with a complex geological history, despite its small size and presumed lack of internal geological activity. The polarization characteristics most closely match those of carbonaceous chondrite meteorites, the most primitive materials found in our solar system, suggesting that 3I/Atlas preserves chemical and physical conditions from the earliest epoch of planetary formation. The mystery of the visitor's composition deepens when spectroscopic observations reveal absorption features that cannot be definitively identified with known molecular species. Several weak absorption lines in the near-infrared spectrum remain unassigned despite comparison with extensive laboratory databases of molecular spectra measured at low temperatures. These unknown features may represent exotic molecular configurations that form only in the unique environment of interstellar space, where cosmic radiation, magnetic fields, and the almost perfect vacuum create conditions impossible to replicate in terrestrial laboratories. Radio observations conducted by the Atacama Large Millimeter Array detect molecular emission lines from trace amounts of carbon monoxide and methanol sublimating from the visitor's surface as it approaches perihelion. The line profiles, the precise frequencies and intensities at which these molecules emit radiation, reveal information about temperature, pressure, and molecular motion within the thin atmosphere that surrounds 3I/Atlas as solar heating drives sublimation of surface ices. The detection of molecular emission confirms that the visitor retains volatile materials despite its billions of years in interstellar space, where cosmic radiation and micrometeorite bombardment gradually erode exposed surfaces. The spatial distribution of these molecular emissions, mapped using interferometric techniques that combine signals from multiple radio telescopes, shows that outgassing occurs preferentially from regions of the visitor's surface that face the Sun during its rotation period. This asymmetric activity pattern suggests either compositional variations across the surface or differences in thermal conductivity that focus sublimation in specific areas. The resulting weak coma, a tenuous atmosphere of gas and dust surrounding the nucleus, remains invisible to optical telescopes but registers clearly in radio observations sensitive to molecular transitions. Detailed analysis of the molecular line profiles reveals Doppler shifts that provide independent confirmation of the visitor's rotation period and axis orientation, as different portions of the spinning object move toward and away from Earth. The emitted radiation experiences frequency shifts that encode information about the three-dimensional motion and structure of the outgassing regions. These measurements complement optical light curves and provide a complete picture of the visitor's orientation and rotation state as it tumbles through the inner solar system. The chemical inventory detected in 3I/Atlas includes several molecules of particular astrobiological interest. The presence of hydrogen cyanide and formaldehyde, both important precursors to more complex organic chemistry, raises questions about the potential for interstellar objects to transport biologically relevant materials between stellar systems. While the extreme cold and radiation environment of interstellar space would prevent biological activity as we understand it, these molecules could serve as starting materials for prebiotic chemistry if delivered to environments with liquid water and energy sources. Laboratory experiments conducted in parallel with the observational campaign demonstrate that the molecular combinations detected in 3I/Atlas can indeed form through purely chemical processes in simulated interstellar environments. High-energy particle bombardment of ice mixtures at liquid nitrogen temperatures produces many of the same compounds observed in the visitor's spectrum, confirming that complex organic chemistry can proceed without biological involvement under the conditions that prevail between the stars. These results support scenarios in which interstellar objects serve as chemical reactors, slowly processing simple molecules into more complex forms during their eons-long journeys through galactic space. The isotopic ratios measured in various molecular species provide additional constraints on the visitor's formation environment and subsequent evolution. The ratio of carbon, 12 to carbon 13 in carbon monoxide, differs from solar system values, indicating nucleosynthesis in a stellar environment with different initial composition or evolutionary history. Similarly, the nitrogen isotope ratio measured in hydrogen cyanide suggests formation in a molecular cloud enriched by material from massive stars that underwent different patterns of nuclear burning than the progenitors of our local stellar neighborhood. Spectroscopic observations continue throughout the visitor's passage, creating a time-lapse record of how its chemical signature evolves as increasing solar radiation drives physical and chemical changes on its surface. The gradual appearance of new absorption features and the strengthening of existing ones document the progressive sublimation of surface layers and the exposure of materials that have remained frozen since the object's formation. Each spectrum becomes a snapshot in the visitor's geological awakening as it experiences the first significant heating in billions of years. The accumulated spectroscopic data transforms 3I/Atlas from an astronomical curiosity into a comprehensive case study of interstellar chemistry and planetary formation processes operating under conditions that differ substantially from those that shaped our own solar system. Every absorption line, every isotopic ratio, every molecular detection adds to humanity's understanding of how matter behaves and evolves in the space between stars, where the building blocks of future worlds drift in the cosmic dark, awaiting their next gravitational encounter with the light and warmth of stellar systems. Gravitational archaeology begins with the mathematics of celestial mechanics. As astronomers trace 3I/Atlas backward through galactic time, using the same equations that govern planetary motion and spacecraft trajectories. The visitor's current trajectory, precisely measured by weeks of astrometric observations, encodes a complete record of its gravitational encounters with massive objects over the past several million years. Each stellar passage, each near miss with a planetary system, each drift through the galactic disk has left its signature in the object's velocity vector and angular momentum, creating a navigational record written in the language of orbital dynamics and readable by those who understand the gravitational choreography of the Milky Way. The process of trajectory reconstruction requires supercomputer simulations that model the motion of thousands of stars within the local galactic neighborhood, accounting for their gravitational influences on small objects like 3I/Atlas as they migrate through interstellar space. The European Space Agency's Gaia mission, which has measured the precise positions and motions of over 1 billion stars, provides the stellar census necessary for these calculations. Each star's mass, velocity, and orbital characteristics contribute to the complex gravitational field that has shaped the visitor's journey, creating a three-dimensional map of gravitational influences spanning hundreds of light years and millions of years. Working backward from the object's present position and velocity, the simulation algorithms integrate its trajectory through the evolving galactic gravitational field, accounting for the slow rotation of the galaxy itself and the orbital motions of individual stars around the galactic center. The calculations reveal that 3 I/Atlas passed within the gravitational sphere of influence of the red dwarf star Gliese 445 approximately 97 million years ago, receiving a velocity change of roughly 3 kilometers per second that redirected its path toward our solar system. Before that encounter, the object followed a significantly different trajectory that intersected with the gravitational neighborhoods of other stellar systems, each contributing smaller perturbations to its interstellar wandering. The red dwarf encounter represents a crucial moment in the visitor's billion-year journey, transforming it from a random wanderer in the local interstellar medium into a directed projectile aimed at our solar neighborhood. Gliese 445, a star roughly 1/10 the mass of our Sun and located 37 light-years from Earth, provided exactly the right gravitational deflection to send 3 I/Atlas on its current hyperbolic trajectory. The precision of this cosmic billiard shot becomes apparent when simulation parameters are varied slightly. Changes of just a few hundred kilometers in the closest approach distance to Gliese 445 would have sent the visitor toward entirely different regions of the galaxy, making its detection by Earth-based astronomers impossible. Further archaeological reconstruction reveals the visitor's deeper history, tracing its path back through multiple stellar encounters over the past 10 million years. Each gravitational interaction modified its trajectory incrementally, creating a complex orbital evolution that resembles a three-dimensional random walk through the local galactic neighborhood. The object appears to have spent most of its interstellar journey moving slowly through the sparse material between star systems, occasionally receiving gravitational kicks that altered its direction and velocity when passing near massive objects. The mystery deepens when the trajectory reconstruction extends beyond 10 million years, approaching the computational limits of current galactic models and stellar position data. The uncertainties in stellar motions and masses accumulate over these longer timescales, creating multiple possible histories for the visitor's origin. Some scenarios suggest ejection from a planetary system within 50 light-years of Earth, while others indicate a more distant origin requiring hundreds of millions of years of interstellar travel. The mathematics of chaos theory apply to these calculations. Small uncertainties in initial conditions amplify exponentially over time, making it impossible to determine the visitor's precise birthplace with current observational capabilities. Spectroscopic analysis provides independent constraints on the visitor's age and formation environment, complementing the dynamical reconstruction with chemical evidence of its stellar origins. The isotopic ratios measured in various molecular species indicate formation in a stellar system with slightly higher metallicity than our Sun, a star enriched with heavy elements from previous generations of stellar nucleosynthesis. This chemical signature suggests origin in a stellar system younger than our own, formed when the galactic disk contained a higher abundance of elements heavier than hydrogen and helium. The object's physical characteristics also encode information about its formation and subsequent evolution. Its elongated shape and complex rotation state suggest either a violent ejection event that imparted significant angular momentum or subsequent collisional modification during its interstellar journey. Theoretical models of planetary system formation predict that objects ejected by gravitational interactions with giant planets should retain certain dynamical signatures that distinguish them from materials ejected by stellar encounters or disrupted by tidal forces near their parent star. Comparison with the orbital characteristics of long-period comets from our own Oort cloud reveals subtle differences that highlight the alien nature of 3I/Atlas. Solar system comets typically approach on nearly parabolic orbits that barely exceed the escape velocity, having been perturbed from their distant orbits by stellar passages or galactic tides. The interstellar visitor, by contrast, arrives with excess velocity that speaks of acceleration in foreign gravitational fields and ejection from stellar systems with different architectures than our own. The gravitational archaeology extends beyond individual stellar encounters to consider the visitor's motion through larger-scale galactic structures during its multi-million-year journey. 3I/Atlas has traversed spiral arms, crossed through molecular clouds, and experienced the varying gravitational fields associated with different galactic environments. Each region contributes its own signature to the object's dynamical evolution, creating a complex interplay between local stellar encounters and global galactic dynamics. Recent advances in computational astrophysics allow astronomers to model these large-scale influences with unprecedented precision, incorporating the effects of dark matter substructure, galactic magnetic fields, and the collective gravitational influence of stellar clusters and associations. The simulations reveal that interstellar objects like 3I/Atlas serve as natural traces of galactic structure and evolution, their trajectories encoding information about the distribution of matter throughout the local galactic neighborhood. The archaeological reconstruction also provides insights into the frequency and characteristics of planetary system disruption events that eject material into interstellar space. The discovery of multiple interstellar objects within a few years suggests that such ejections occur regularly throughout the galaxy, creating a constant population of wandering worlds that migrate between stellar systems. Each visitor represents a sample from this vast galactic ecosystem, carrying chemical and dynamical information about planetary formation processes operating under diverse stellar conditions. Statistical analysis of the growing population of known interstellar objects reveals patterns that constrain models of planetary system architecture and evolution. The size distribution, velocity dispersion, and chemical characteristics of these visitors provide direct observational evidence of how planetary systems form, evolve, and occasionally disintegrate under the influence of stellar companions, migrating planets, and external gravitational perturbations. The gravitational archaeology of 3I/Atlas thus extends far beyond the reconstruction of a single object's trajectory, becoming a window into the broader processes that shape planetary systems throughout the galaxy. Each calculated position, each gravitational encounter, each stellar passage adds to our understanding of how matter moves through the cosmic web of gravitational influences that connects all stellar systems within our galactic neighborhood. The irony of this archaeological endeavors lies in its fundamental limitations. The very gravitational processes that make trajectory reconstruction possible also ensure that the visitor's ultimate origin remains forever shrouded in the mathematical uncertainty that characterizes chaotic dynamical systems. The farther back in time the calculations extend, the more the possible histories multiply, until the object's birthplace dissolves into a probability cloud spanning dozens of stellar systems and millions of possible formation scenarios. Yet within these limitations lies a profound truth about the nature of galactic evolution and the interconnectedness of stellar systems. 3I/Atlas represents not just a visitor from beyond our solar system, but a messenger from the vast network of gravitational relationships that bind together the stars within our local galactic neighborhood. Its presence in our skies testifies to the continuous exchange of material between stellar systems, a cosmic recycling program that has operated throughout the galaxy's history, redistributing the products of stellar nucleosynthesis and planetary formation across interstellar distances. The visitor continues its passage through our solar system, unaware that its trajectory has been deconstructed and analyzed by the inhabitants of a small rocky planet. Its billion-year journey reduced to equations and orbital elements that reveal the gravitational archaeology of its wandering path through the galaxy's stellar population. Pristine chemistry unveiled emerges from laboratory analysis as Earth's most sophisticated spectrometers dissect the reflected sunlight from 3e/8ls, revealing molecular combinations that